So if you think cholesterol is what causes atherosclerotic plaques and blocked arteries, which I did too, by the way, because that's what I was taught at school and university, then I'd like you to explain the following if cholesterol really does cause it. First off, on the hypothesis that cholesterol equals blocked arteries or atherosclerosis, we have to ask, where is cholesterol? Obviously, it's in the blood, but specifically, it's in the whole of the blood, right? It's everywhere. So if it's everywhere, then that hypothesis of cholesterol equals atherosclerosis would mean that atherosclerosis is also everywhere because the blood is. But is it? If it is, then obviously that hypothesis could be deemed as probably correct. But it's not the case, okay? I'll get a picture on screen now of the body's vasculature. The venous side, or the side of the veins, doesn't develop atherosclerosis, even though it has, the same amount of cholesterol coursing through it as the arterial side. Why is that? If cholesterol equals atherosclerosis, then why is it not in the veins when it's there too in exactly the same amount as the arteries? Well, clearly that theory needs banishing from our education system, frankly, and I'm going to show you the exact step-by-step mechanism as to how the blockages actually occur, as can be seen and predicted consistently in clinical practice, like with my own patients. Now, when I spent time in the NHS, which is the National Health Service for those not in the UK, I couldn't have these conversations with my patients because I think I'd have been fired for saying things which are outside of what's taught in medical school. But I left that and all hospital work, and I only work privately now, where I can spend longer amounts of time with each patient and I can actually treat them properly without saying or doing things that are designed to make money for big pharmaceutical companies as the priority. So I'm going to work through the atherosclerotic plaque, or ASCVD, atherosclerotic cardiovascular disease, pathophysiology, how it comes about, from start to finish. And I'm going to use basic logic at every stage to show you that you honestly don't have to be a doctor, even though I am one, to take control of your own health. To start with, I'll get a diagram here of the vasculature. The side with veins, the venous side, is going to be much lower pressure than the arterial side. The arterial side is supplied by the left ventricle of the heart. This might be right on camera. That's the bit which generates enough force to get it all around the body. Where the arteries become veins, here we have capillaries that deliver oxygen to the cells that need it. And they're low pressure too. And they're also really small to reach into tiny places, as you can imagine. Once the oxygen's been offloaded, the deoxygenated blood then makes its way back to the heart. And there it gets sent by the right ventricle to the lungs to pick up oxygen again before repeating the cycle. Taking a big picture look at this diagram, I'll say it again. There's no atherosclerosis or heart disease or vessel disease in the venous side. It's all arterial. This is the first mechanistic step in disputing the thought that LDL cholesterol or cholesterol in general has a causal link to blockages. If the same cholesterol or blood is everywhere, then that theory should give this blockage issue everywhere as well. This is why we can safely say that there's no direct causality between these two things. And that's pretty much the end of the argument, to be honest. When I've had this conversation with fellow doctors at conferences or in clinics, even cardiologists, by the way, they have no response to this logic that I put forward to them. Now, that doesn't mean that LDL cholesterol isn't involved in some way. It could still be a contributing factor whilst we're still working our way through this step by step and thought by thought. But our next step in this logic is to ask, well, what's different then between the arterial and the venous sides? Well, the actual epithelial cells that line the vessels and actually contact the blood, these vessels aren't really that different. The structure's pretty much the same. The musculature, keeping the vessels stable, which is called smooth muscle, it's a bit bigger on the arterial side, and that's because there's higher pressure, so you need a higher ability to withstand that pressure, as I'm sure you can understand. The walls, I'd say, are a bit thicker too overall. We can measure that, but we're kind of clutching at straws here. The physical structure is really just not that different at all. But remember what I said before, the biggest difference is the pressure inside the vessels. We're also going to add another concept here called shear stress. This is to do with the turbulent flow and how different directions of flow can interact with each other and the environment holding them in position. Pressure is basically a measure of how much force is being exerted on the vessels from the blood on the inside. That's why the formula for pressure is force divided by area. and why you get pressure units like pounds per square inch, force per unit area. And the aorta is under the most pressure because it's the first bit the blood goes into after the left ventricle pumps blood out of the heart. This is why the vessel cells here are more likely to get damaged if there's high blood pressure in you as an individual. They're taking this pounding from the pumping constantly and adding to the pressure. It's going to give even more of a pounding. And I hope you can see too that this isn't complicated, by the way, to understand or follow. It's all pretty logical at the end of the day. So if the pressure from the heartbeat is combined with a raised baseline blood pressure as well, then eventually you can actually get inflammation of these cells. If you get punched in the face repeatedly, like a boxing match, then as the rounds go on, your face is going to look more and more swollen and inflamed because of the physical and mechanical damage that's done. And you can imagine the cells in the vessels getting punched constantly from natural pressure being increased by high blood pressure on top of that. So to recap and try to kind of summarize what we've gleaned from our logic so far, to create atherosclerosis, one of the things we need is some kind of inflammation of the epithelial cells lining the arteries, and we can get this by increasing the blood pressure to then increase the physical force on the cells to damage them and then cause an inflammatory response, which is where the body tries to protect itself. Now, we don't get this on the venous side because we don't have this type of damage there due to the pressure being much lower. Those punches to the face, they're not happening in the veins, they are in the arteries. So let's carry on. Let's take a look at the variation in blood pressure, right? You get this all throughout our vasculature. I'll get a diagram here that shows the pressure when the blood leaves the heart as being very high. Now, obviously, it's going to be very high at this point. But as you get further away, the pressure reduces and the pulsatile nature of the flow starts to reduce in size. And then you get to the smaller arteries, the pulses actually just stop. And you get this more constant flow, which is called laminar flow. This is basically like, it's like a normal steady stream of traffic instead of stop-start. And after that, you've got the capillary beds where oxygens are floated, like I said, and then you enter the venous system. And the pressure, as you can clearly see, is well, hopefully, depending on which diagram I get, is lower and lower the further you are from leaving the heart and the closer you are to returning to the heart with deoxygenated blood. And this kind of shows you, in a really clear way, the lack of pressure leading to lack of damage in the venous side. Now, again, I'm going to add to our logic here. I'm going to throw in the study of fluid dynamics. In simpler terms, the study of turbulent blood flow within the arterial vessels. We can't really do this for the venous side because the blood there just flows like a steady stream of traffic constantly, laminar flow. But on the arterial side, we've got things like Y-shaped junctions. I'll get a picture of one on the screen here, actually. This Y-shaped junction is termed a bifurcation. The initial portion just splits into two, and you get bifurcations to things like teeth roots, where a single root can split into two. Now, after the split, generally you get one side bigger than the other. And the arrows that hopefully you can see on the diagram show you the direction of the flow of that blood when it's in this bifurcation. It's not that different to what happens in the world around us, in things like rivers, and how the water in them flows in specific ways. The physics principles of fluid flow are basically the same there and here. When the flow hits the Y part of the bifurcation, it gets pushed sideways into the side of the vessels, and that's how it gets this kind of spiral or swirling effect. And as you'll come to see, this turbulence is another factor that's needed in order to achieve atherosclerosis. Now, when the blood flows through vessels with pressure, that pressure is going to push outwards on the vessels. Okay, so you've got something called shear stress as well, which I've mentioned before. I've mentioned that in, for example, my big hyaluronic acid video when I talked about the manufacturing of it. But you get it in vessels as well. It's the force exerted by the moving blood on the inner walls of the arteries. Basically, as the blood flows, it creates this tangential force that acts parallel to the surface of the arterial wall. And that's critical in regulating vascular function and health. If you have that, you help maintain the integrity and flexibility of the arterial walls. And you can promote release of things like nitric oxide. That keeps them dilated. And areas like this have no atherosclerosis, surprise, surprise. But if you have low shear stress, then you do have atherosclerosis. When you look at the diagram, you can see there'll be areas where the blood turbulently swirls, like in bifurcations, instead of flowing parallel to the vessels. Now, these swirly areas have low shear stress, and as you can see, the areas highlighted then have a higher adhesion of monocytes, which are cells from the immune system, and a higher permeability to LDL cholesterol particles. So to recap, I know this, you might need to watch this more than once, but to recap, we've got damage from high pressure, as well as increased amount of turbulence, which then gives us lower shear stress. This then allows that blood to hang around instead of making its way straight through. And it seems like this is what allows the LDL to then place itself in the small gaps that appear from damage between the vessel cells, right? The high pressure seems to cause damage that makes this small gap like a sort of break or fracture, if you like. And once this happens, we can get inflammatory markers which can then increase the permeability even more. Okay, at this point, even more SDL particles can get stuck in there. And these are small, dense LDLs. You also have LB, which is large, buoyant LDL. The fact that they're A, large, means that they can't fit into the same gap, and B, buoyant, means they float, so they aren't going to be possible to tie down in the same way. Now, don't jump to conclusions, though, right? Just the actual getting stuck in the gap isn't necessarily the issue. They're positioned there now because the underlying cells have been damaged and they need repairing. Now, if you're going to rebuild or repair cells, then you need to make the membrane which cells are made of. And take a guess what that membrane's made of, amongst other things. Cholesterol. And how convenient is it that some has just landed there, ready to help out and donate some building blocks to repair. Now, in a normal situation, that repair just takes place, and then the LDL can be released, and everyone's happy. But in the abnormal situations, we have a different situation. In an abnormal situation, or an abs-normal situation, sorry, that was so bad, but we have longer-term blood pressure or chronic hypertension, to use medical terminology. These LDL particles, they never get released, and we get oxidative damage over time, where the LDLs stay there for ages, and the oxygen flowing past, that can cause oxidation of the LDL matter. And this is another factor why we don't see in venous sides, because the veins don't carry oxygenated blood. Now, we can also get damage from glucose, because glucose glycates things, which is where it kind of attaches onto stuff and prevents that stuff from doing its job, like a nagging child that's attached to you and slowing you down at work. And when we measure something called a HbA1c on a blood test, we're measuring the glycation of hemoglobin. Glycation is not a good thing, the glucose attaching to the hemoglobin, and it can cause lots of harm. If it happens to hemoglobin, then it can't deliver the oxygen to your cells as well. I won't go into diet and glucose too much in the video, but I will say that this is one reason why watching carbohydrate intake is so important. And if you get to the point where you can be considered as having a glucose uptake into cell, or not having glucose uptake into cells, even with insulin around, which is what we call insulin resistance to make it easy, then that glucose lingers in the blood even longer, and it can cause even more damage. As a carnivore, I'll never have to worry about this because I just don't eat carbs. My body makes glucose from fatty acids or amino acids whenever it needs, so it'll always make the exact amount it needs. It's not going to make so much it causes damage to itself. Obviously, we wouldn't have evolved that way. Now, if this process with the vessel damage and LDL placement goes on, then the body starts to create an immune response too, right? You get these things called macrophages, which are the cells of the immune system, and they turn up like police at a crime scene, right? And now this is full-on atherosclerosis. Our bodies have put that LDL there for a particular purpose. It's supposed to be there. Why would we make something that causes us to react badly as soon as it's made? We would have died out long ago as a species if that happened. There are many things I can say about diet here and its role in this pathophysiology. But I'll leave it for another video because there's still people out there that think veganism is really healthy. It is in the short term, but I won't go on. Now, I want to show you the actual formation of these plaques so you can actually see for yourself the real life manifestations of all these logical steps we've gone through today, and also see for yourself that these logical steps we've gone through are actually correct. I'll get a diagram of an arterial bifurcation on screen for you now. You should be able to see the areas with high and low shear stress, and we can see then the actual plaque formation sites too. What I want you to take from this is the fact that the real life observations completely back up everything in these logical steps that we've gone through today. We've gone through it in a systematic and methodical and predictable way, along with common sense, some reasoning behind why these plaques and blockages might be happening, and now we can see what actually happens in real life clinical practice too, in a completely predictable and formulaic way. I see these things in my own patients when we get let's say a CAC or CAC scan done of the vessels. In fact, part of the reason I'm making this video is so my patients don't have to remember everything I say, and they can just watch this back instead as a reference, because they always ask me about cholesterol. Other portions of the vasculature have the same blood, with the same cholesterol, with the same oxygen, with the same glucose, and clearly no plaques there at all. It should be obvious now that clearly some kind of mechanical damage is 100% required for atherosclerosis to initiate. If you're wondering why a tiny bit of plaque forms at the split point of the bifurcation, by the way, it's because the currents and turbulence change once you have plaques built up in the bigger areas first, and then it can have a knock-on effects elsewhere too. To expand on this real-life clinical practice view so that we can test all the step-by-step logic that we've gone through here, there's a diagram, which I'll get up, of the areas where we actually find atherosclerotic plaques. Surprise, surprise, it's only in the larger arterial vessels. And if we distill what's going on even further, it's only in the areas where we have lower shear stress in these places as a result of turbulent flow, which allows for some form of blood to hang around, stasis. And the areas where there's higher shear stress, where it's flowing past nicely, there's no pathophysiology, there's no pathology going on there. So I hope you guys see why it's so ridiculous to say the blanket statement, LDL cholesterol is the cause of atherosclerosis. It's actually quite incorrect. And hopefully, as you'll see now, I couldn't care less about my lipid panel or my blood tests, which show that I have very high LDL cholesterol. Our bodies have genes that have evolved over millions of years to protect us. If cholesterol was bad, how would we have evolved to still be alive now? It makes no sense that our bodies would do something that ends up killing us. It's also why looking at blood results and lab tests, to a certain extent, in some cases, can be a useful exercise. We've hopefully now completely dispelled the notion for you that cholesterol equals heart disease. I could go on and talk about ApoB, which I know a lot of you are worried about because people like Peter Attia say it needs to be low. However, we can go through this exact same exercise of making logical step-by-step distillations to come to the same thought about ApoB too. You don't need to worry about it. Your body's put it there for a reason. Maybe that'll be a video for another day. There's different doctors that will always say different things because in medical school or dental school or nursing school, whatever, we don't get taught things like statistics to any meaningful degree. And I'm saying that from a personal experience of university. And as a result, clinicians don't understand the importance of understanding the difference between association or correlation and actual cause and effect, which is what we can derive as direct risk. You also don't pay attention to making sure there's a sound basis of control over independent variables, which is more complex than it sounds for most. I appreciate that. Now, I'm not saying also that I'm any better. I'm not a statistician by any means. But I do try and remind myself of association versus causality in risk whenever I can. And through videos like this, I like to show actual mechanistic steps, which you can see for yourself. And that can also be tested in clinical practice for veracity every day. Seeing what I've shown here in my clinical practice with real patients shows me that what's been shown here, which isn't 100% of the subject, by the way, is true. I know some may disagree with certain bits, and that's always going to happen. But I'm saying it as someone that actually sees patients with this exact phenomenon day in, day out. Now, please understand that this video is once again not designed to convey the whole subject in its absolute entirety. There's a reason medical school is years. There are indeed things I've left out because I don't want it to be longer than it already is. But I hope you've learned something from it.